In 3.3, we are shifting gears. In previously, we looked at population percentage. What was the variable for population percentage? Pi. And that's when we were asking categorical data. Yes, no questions. You know, what is your favorite color? Do you like your parents? That sort of stuff. So now we're moving on to quantitative data, where we're asking a question where the answer is a number. And then we're going to be taking the average of that number, and we're going to introduce, when you ask a yes-no question, there is no standard deviation, right? It's just 40% of the people said yes. And then we created a standard deviation to do z-score testing, but that number was based off of how many people you talked to and what the population percentage was. And it wasn't a real standard deviation. It was kind of a standard deviation of a bunch of different samples. So, but when you ask quantitative data, for instance, how old are you, we can find the average of that set, and we can also find the standard deviation of the set. So here, every 10 years, the federal government conducts a population census where they collect data about every person in the country in a certain state, and I totally made this up. The average age is 39.6 with a standard deviation of 19.5, and that is the histogram. So does it look like 28 to 32-year-olds die more often than everybody else? Probably not. What's probably going on? We had some kind of crisis. Okay. It has to do with the number of births, right? So we have these kind of booms, the baby boomers and then the not so baby boomers. So this is a histogram that is not normally distributed. So number one asks, what variable will we use for the average age of the population? Do you remember this from the Zybook? You're 0 for 2 today. Mu. So number one is this weird looking, it kind of looks like an M if you tilt your head a little bit, or it's a U with a line down the side. That is the Greek letter lowercase mu. And mu is a parameter. What does a parameter mean? Not a sample. It is a number that describes the population. So number one is mu. Okay, number two. What variable will we use for the standard deviation of the population? Lowercase sigma. And it's a circle with a line on it. That is lowercase sigma. Okay? So, we travel to this state, and we do a simple random sample, which is really hard to do, by the way. And we talk to 200 people. And we ask them how old they are. What are our observational units? People. Right? That's who we are talking to. We are studying people. And what is the variable of interest? Their age. We're asking them, that's the question we're asking. How old are you? What symbol would we use to label the average of the sample? Hey, there you go. You got one right. So the sample average is X bar. And what symbol do we use to describe the sample standard deviation? It doesn't get a cool symbol. It's just S. So the sample standard deviation is S. Now these are statistics. Statistics are numbers that describe samples. Okay. So if we talk to 200 people and we do a simple random sample, what would we expect the average of our sample to be? Well, if our sample is representative of the population, then our sample sample average should be close to 39.6, the population average. Now, is it going to be perfect? No. But if you had to guess, that would be your best guess. Does that make sense? We would expect our sample average to be the same or close to the population average. Okay, does that make sense? All right, now this is going to get a little bit confusing, so make sure you pay close attention. And if you don't understand an answer, please let me know. So, would we expect, what would you expect the standard deviation of the sample to be? 19.5. So, if we do our work correctly, our sample should look just like the population, just with fewer people. Does that make sense? Okay. So, number 9, would we expect the sample to be normally distributed? No. So if we pull from this group of people, now we might only talk to 1 in 100 or something. So we might talk to this many people. Oh, that should probably. So our sample should look just like the population. And if we do a simple random sample, chances are that's what's going to happen. So our sample average should be relatively close to the actual average. Our sample standard deviation should look very similar to the population standard deviation. And the shape of the sample histogram should look the same as the shape of the original histogram. Okay, does everybody understand that? Now, will talking to more people change any of those three things? Will talking to more people change the sample average? It shouldn't, not much. I mean, I guess it'll go up and down a little bit, but it should be about the same. Will it change the sample standard deviation? That is the average distance from the average. No, that should stay the same. Will it change the shape of the histogram? Well, I mean, I guess it'll get taller, right? But the shape should be the same. Okay, we good there? Our sample should look like the population. Okay. Now, suppose that many, many samples, each containing 200 people, were conducted, and the averages from each sample were compiled into a histogram. So I do a sample of 200, you do a sample of 200, and you and you and you, and lots and lots and lots of people. And then we graph our averages. Would you expect the histogram to be normally distributed? Yes. Okay. What is the name of this type of histogram? Anybody remember? Sampling distribution. Did you look? Well done. I believed in you. Trust me. So this is called a sampling distribution. Okay. So my original histogram looked like this. Right? This is my population. Any sample I conduct properly should have the same basic shape and the same basic average and standard deviation. Okay? But if I take a sample, and that is my sample, so if I graph X bar and number, so I do a sample, you do a sample, everybody does a sample, it will end up looking something like that. Now, does the sampling distribution actually exist? No. It's a theoretical idea, right? Are we really going to go out and have 5,000 different people each do a sample of 200 people from this state? No, you might as well just talk to everybody, right? So this sampling distribution does not actually exist. But if we were to conduct all of those samples, then it will be normally distributed. What does one dot on the original histogram represent? A person and their age. What does one dot on the sampling distribution represent? It is the average of a single sample containing 200 people from the original population. Does that make sense to everybody? Okay, now, what is the standard deviation of, oh wait, there's another question, I skipped one. What would we expect the average of all samples to be? 39 point, was it 5? 6. Okay, so the average here is 39.6. If I take a sample, the average of the sample is probably going to be close to 39.6. If we create the sampling distribution, the average of the sampling distribution is probably going to be about 39.6. Okay? But what is the standard deviation of the sampling distribution? So the SD here was, what was it, 19.5? Okay, and what was the standard deviation here? It's probably going to be about 19.5 because the spread is the same. The spread here is roughly the same as the spread here. But what is the standard deviation of this? It's going to depend. It's going to depend on two things. It's going to depend on this, and it's going to depend on how many people are in each sample. Okay? Now, this textbook uses a phrase that I've never heard of before. Okay? In every text I've ever dealt with, it was always called the standard error. And I did a text search in this textbook, and the word standard error does not exist. So instead, they're calling it the SD of the statistic. Yeah. And I've never heard that before. So what is a statistic again? It's a number that describes, not the population, a sample. Okay? So this is not the standard deviation of the sample. It's the standard deviation of the sampling distribution. Does that make sense? So this SD is 19.5. This SD will probably be about 19.5. Okay? But if we create the sampling distribution, then that sampling distribution is going to have a standard deviation that we call the SD of the statistic. And maybe they call it something else later. But the SD of the statistic is a formula which is, it was in 3.3 in Zybook. Anybody remember it? It is S, well, it's actually not S. It's sigma divided by the square root of n. So the standard deviation of the sampling distribution is going to be 19.5 divided by the square root of 200. Now, n, is n the number of dots in this? No. What is n? It's the number of dots in this. right? N is the number of people you talked to. So we take 19.5 and we divide it by the square root of 200. So 19.5 divided by the square root of 200, and I get 1.37. Okay? And that is going to be in, age. So I get the SD of the statistic is 1.37 years. What does that number mean? Well, let's ask this first. What does this number mean? Means that the people in the state, on average, are about 20 years away from being 39.6 years old, right? And then we can do all that stuff where 68% are between this number and this number, okay? So, what does this tell me? The average, not the average age, the average of the average ages is about 1.3 years away from the average of 39.6. Okay? Do you see where we're headed with this? Well, we're not going to do it on this worksheet, but the goal is to start doing z-tests with averages. So, are we ever actually going to know the population numbers? Right? Probably not. If I told you the average height of all males in the country is 71 inches, okay? You're going to run out and do a sample, and you're going to compare your sample to my claim and do a null hypothesis, and then you're going to decide if you think I'm right or if you think I'm wrong. Where is that claim going to come from? Well, we are not going to be able to look at this. If we knew that, we wouldn't bother doing a sample. So instead, we're going to look at our sample and we're going to build a sampling distribution, and then we will use the average and the SD of the statistic to calculate a z-score, and that z-score will give us a p-value, and that will decide whether my claim was right or wrong. So that's where we're going. That's exactly what we did with percentages, but now we have this extra formula for the standard deviation that we didn't have to worry about before. Actually, there was a formula, it was just a different one. Okay, does that make sense? All right, so that answered, so 13 is 1.37. What do we call that number? The SD of the statistic. All right. Suppose that many, many samples, each containing 500 people, were conducted on the averages from each, and the averages from each sample were compiled into a histogram. Would you expect this histogram to be normally distributed? Yes. Why? Well, not because of more people, because it's a sampling distribution. Just like number 11. Okay. What would you expect the average of all samples to be? It's still 39.6. That hasn't changed. What would you expect the standard deviation of all samples to be? So now I need to change this. So 19.5 divided by the square root of 500. What happened? So the last question says, why is the standard deviation of this sampling distribution smaller than that of the previous one? And that's true. We have more people, but does it make sense that it got smaller? If you talk to more people, what do you expect to happen? To get closer to the true value. So in our original sampling distribution, right, this graph here, there's a little bit of uncertainty because we only talked to 200 people. But when we talk to 500 people, we get a different graph that looks like this. Does that make sense? we are more sure about our 500-person sample than we are of our 200-person sample. And that is indicated in the standard deviations. So 0.87. Okay, let me see. I'm going to go back a couple chapters and see if this makes sense. So don't go ahead yet. If we only talk to 200 people, then our uncertainty is 1.37 years, which means 68% of all samples will be up 1.37 years or down 1.37 years. But if we increase our sample size from 200 to 500, our uncertainty goes down. Does that make sense? And in fact, our uncertainty is almost half of what it was before. So the more people you talk to, the less uncertain you're going to be. So if we were doing a null hypothesis, is it easier to reject the null with 200 people or 500 people? 500, because the standard deviation goes down, which makes our z-scores go up, which makes our p-value go down. And the more people we talk to, the more our uncertainty shrinks until we talk to everybody, and then our uncertainty is 0. Does that make sense? All right. I think that's everything you need to know. Get to work. I don't think we'll be logging back on, Garrett.
Okay.
Right. Yeah.
Alrighty, see ya.